Angela Crowther works for Expedition, a structural engineering company responsible for some highly innovative buildings, such as the 2012 Olympic Velodrome. In this video clip, she talks about the increasing importance of sustainability and the role of mathematics in low-carbon design.
We all know about global warming and greenhouse gases and the effect of carbon on the environment. And the construction industry makes a massive contribution to the amount of carbon we're emitting. Sustainability has very much become a buzzword and something we need to tackle. Now, our work on the 2012 Olympics, we were responsible for designing and building the velodrome. What we did was think about how we could make a very sustainable structure, how our design could be very efficient material-wise. I came in very much at the tail end of that design and build process, so it was my colleagues that were responsible for that. But what I have done is gone back and tackled the numbers, looked at, in retrospect, how sustainable were we, how efficient is our building, and is it something that we can use as a case study of best practice for future generations.
As a starting point for her calculations, Angela referred to standard data for the environmental impact of using various different types of building materials. This impact is expressed as tonnes of embodied, that is to say emitted carbon, per tonne of building material. Embodied carbon takes into account all the adverse environmental factors associated with the material throughout its lifetime.
Bath University produced a compiled list of different materials and the amount of embodied carbon that exists within each of them. Now, embodied carbon is all the carbon that arises from the construction process. So from mining the materials in the first place and sourcing them, to transporting those materials to the factories and warehouses, to actually undertaking the techniques of processing those materials, that all takes energy and emits carbon as well, to then transporting them to the building site, to all the other materials and processes that are used in actually constructing the building, to their in-use life cycle at the end. So all of those processes are evaluated to determine how much carbon is used at each stage. So when considering the actual velodrome and the amount of embodied carbon within that, the way you tackle that is by taking the known quantities of different materials. So for example, we're using a steel cable net roof. I can take the number of cables we've got in the roof, the length of the cables, the diameter of the cables, at which point I can create a spreadsheet which tells me the tonnage of total cables in that roof. I can then say, I know that they're this type of steel, and I can go back and look at the tests people have done on that type of steel to establish a baseline figure for the embodied carbon in them, and quite simply apply that number as a factor to my tonnage, at which point I'll come out with an answer that says, okay, in this roof there are so many tonnes of embodied carbon, or CO2, so many tonnes of carbon dioxide per tonne of actual steel material. You go through and you do that for, first of all we started off with our steel cable net roof, then we can go down and look at our concrete columns and our piers and the actual seating, right down to the foundations in the ground. So you go logically through the building, you apply the different factors to the different materials, and at the end you're going to get one big figure. So our total number for the velodrome was 6,800 tonnes of embodied carbon. This, as a number itself, is pretty meaningless actually. What does that mean? You can't visualize it, you don't know what it measures up to. So to try and create some meaning on a human level, what I then did out of interest was go back and work out how much embodied carbon in a cup of tea. I then worked out how many people there are in Britain drinking cups of tea per day, and I actually found out that that 6,800 tonnes of embodied carbon in the velodrome equates to every tea drinker in Britain just drinking tea for only 3 days, which I found quite an astounding fact actually. The type of roof structure we used was quite a pioneering technology. It's a cable net roof. That basically means that the Pringle shape we get for the velodrome roof is come from tensioning the cables and from finding a form that is the most efficient. The loads that are applied to the roof are carried down the building in the most efficient manner possible. It's from doing this and form finding to find that most efficient shape that you're able to reduce the amount of material in the roof, because you're only putting material where it's needed, where the load needs to travel. The developers didn't actually want to use a cable net roof. It hadn't been used before, it's a bit risky, it's pioneering technology. And so it's quite an interesting story that we won through in the end, and we've made such a sustainable building because we were able to go away and demonstrate that, okay, the costs might be slightly higher or the initial risks might be slightly higher, but actually the benefits architecturally and materials-wise, that whole story offsets it. And so I think the biggest lesson that we've learned actually is that Rome wasn't built in a day, and it wasn't built by one person. So you have to work holistically across different teams and different specialisms to be able to make informed decisions, of which sustainability is just one.